A fetus develops with an umbilical artery oxygen tension of approximately 3 to 4 kilopascals, roughly 1/3 of the partial pressure required for adult survival, circulation. This localized deficit in alveolar oxygen triggers a synchronized vasoconstriction response across the network of fetal pulmonary arterioles. The result is a high pulmonary vascular resistance, or PVR, that spans the entire fetal lung. High PVR acts as a physical barrier, forcing 85 to 90% of right ventricular output to bypass the lungs. This flow takes two escape routes, the foraminal and the ductus arteriosus connecting the pulmonary artery to the descending aorta. Fetal cardiovascular survival is an active, high-pressure systemic shunt. It relies on a continuous biochemical engine that keeps the pulmonary vessels locked shut. This barrier is maintained through a complex local mechanism within the pulmonary arterial smooth muscle cell, or PASMC. While systemic vessels dilate in response to metabolites like H+ and CO2 to increase blood flow, the pulmonary circulation responds to hypoxia with rapid vessel constriction. The mitochondria act as the primary sensor. A drop in oxygen alters the electron transport chain, shifting mitochondrial reactive oxygen species production. This redox shift inhibits oxygen-sensitive potassium channels, stopping outward ion flow. Retaining these positive ions depolarizes the resting membrane potential. This electrical shift represents the acute phase of HPV, occurring within seconds of the initial hypoxia. By trapping potassium ions, the cell translates a chemical oxygen deficit into an electrical shift that initiates contraction. The depolarized membrane causes L-type voltage-gated calcium channels to snap open, allowing extracellular calcium to enter the cytosol. This calcium influx acts as a secondary trigger moving toward the cell interior. It initiates calcium-induced calcium release. The incoming ions bind to ryanodine receptors on the sarcoplasmic reticulum, triggering a massive release of stored calcium. This sequence causes a rapid intracellular calcium increase. The free calcium binds to calmodulin, forming the active calcium-calmodulin complex. This complex activates myosin light chain kinase, or MLCK. MLCK phosphorylates the myosin light chain, initiating actin-myosin crossbridge cycling and cellular contraction. The endothelium amplifies this signal. Hypoxia downregulates endothelial nitric oxide synthase, which reduces the production of vasodilatory nitric oxide. Simultaneously, the release of endothelin-1 binds to ETA receptors on the smooth muscle cell, helping maintain high vascular tone. While this acute contraction occurs within minutes, prolonged hypoxia over hours or days is maintained by gene transcription via hypoxia-inducible factor 1. This precise sequence of calcium and kinase activation generates the immense pressure required to maintain the fetal circulatory shunt. At birth, the dramatic first breath physically expels residual lung fluid, immediately filling the collapsed alveoli with a rush of atmospheric air. This results in an immediate spike in the alveolar oxygen partial pressure. The mitochondrial redox state normalizes, causing the potassium channels to open. Potassium ions rapidly exit the cell. This exit of potassium hyperpolarizes the membrane, causing the L-type calcium channels to snap shut and terminate the calcium supply. Endothelial activity also reverses, as increased nitric oxide and prostacyclin production flood the local vessels. The relaxation of the smooth muscle cells causes pulmonary vascular resistance to drop. With PVR now lower than systemic resistance, the right ventricular output enters the pulmonary capillary bed. The shifting pressure gradients force the functional closure of the foraminal and ductus arteriosus. A single breath dismantles the fetal shunt, transitioning the infant from a parallel circuit to the adult configuration. This fetal survival mechanism remains active in adults to protect against localized hypoxemia. One lung ventilation during thoracic surgery provides a direct clinical application of this response. Blood flow is diverted away from the collapsed lung to maintain systemic oxygenation. HPV in the collapsed lung minimizes intrapulmonary shunting by forcing blood toward the ventilated alveoli. Volatile anesthetic agents can interfere with this protective pathway. At concentrations greater than 1 mAc, these agents inhibit the vasoconstriction response in a dose-dependent manner. When HPV is inhibited, vessels in the collapsed lung dilate. Deoxygenated blood mixes into the systemic supply, resulting in arterial hypoxemia. Intravenous agents like propofol do not interfere with the potassium and calcium cascade, leaving the HPV response intact. The intracellular cascade within the PASMC provides the biochemical framework for managing thoracic anesthesia. Understanding these mechanics allows for the active management of the physiological systems that sustain oxygenation during surgical lung collapse.